Hey guys, welcome back to a new video. In this session, we'll be solving step by step two real-life applications on using the centripetal force. We'll be calculating how sharp of a turn a fighter jet can take in order to avoid fighter pilots from passing out as the consequences of the G-forces. And we'll also see why the rotation of the Earth makes it such that you're actually heavier than you think. For both of these problems, we'll be using the theory of uniform circular motion. And as always, if you have any questions along the way, feel free to ask them in the comment section below. Or you can also join our Discord server to freely interact with fellow students and myself about anything mathematics or science related. And with that, let's dive right into it. And before we tackle the real-life applications, let me first do a brief recap of the quantities used in uniform circular motion, just to get everyone on the same page. You can of course skip this section and go directly to the exercises. Any circular motion is of course characterized by a circular trajectory. And the circular trajectory is of course defined by its radius r. When we travel along this trajectory, we can connect the initial and the final point with the center of our circle. Doing this, our trajectory defines an angle theta, which defines the portion of the circle which we traversed. Given these two fundamental quantities r and theta, we can of course calculate the effective length that we traversed along the circular trajectory, named s. And this gives us our first fundamental formula that s, so the length along our trajectory, is equal to the radius of our circular motion multiplied with the angle theta. And I explain why this exactly is in another video. Because we are moving along a trajectory, there is of course also a velocity. And in this case, we have the tangential velocity, which is always tangent to the circular trajectory. And the magnitude of this tangential velocity gives us our second fundamental formula. So the magnitude of Vt is simply equal to, of course, the time derivative of the distance that we traversed along our trajectory. And using the first formula, we find that this is equal to the radius multiplied by omega. And omega is the angular velocity, so the rate of change of this angle theta. Now, because in this video we're looking at uniform circular motion, we know that the magnitude of this tangential velocity will be constant at each point in time. This means that this will simply be a constant. Now we also know that even though the magnitude of our tangential velocity is constant, we still have an acceleration present, namely the centripetal acceleration, which will always be perpendicular to the trajectory and pointing towards the center of the circle. And again, why this exactly is, I cover in other videos. What is important here is that the magnitude of this acceleration is equal to the magnitude of our tangential velocity squared divided by our radius r. And these are the three formulas related to uniform circular motion that we will use to solve the application problems. And because of course we're dealing with forces, we also take into account Newton's second law, which simply says that the net force acting on an object is equal to this object's mass multiplied with its acceleration. So a net force results in an acceleration. And more specifically, we have that the magnitude of the centripetal force, which is associated with circular motion, is equal to the mass of the object multiplied with the magnitude of the centripetal acceleration. And because we know the formula for the centripetal acceleration, we know that the magnitude of the centripetal force is equal to m multiplied with the velocity squared divided by the radius of our circle. And at this point, we have all the ingredients that we need in order to solve the application problems. In this first exercise, we are considering an F-18 fighter jet, which in general flies at a velocity of around 2,000 kilometers per hour. And in particular, we consider the case where it suddenly receives orders to make a U-turn. Now, a U-turn, of course, is a turn of 180 degrees. Now, because this fighter jet is flying at such high velocities, the fighter pilot that is flying the jet will experience a lot of g-forces when it actually makes a turn. You can compare it when you're driving at a quite large velocity on the road and you suddenly have to make a turn. What you experience is a force dragging you to one side of the car. Now, because humans did not evolve to be in such extreme situations, the maximum g-force that a human can handle before passing out is 9. Now, what does this mean? It means that the force experienced by making a turn is 9 times larger than the force of gravity that we all experience here on Earth. This means that if you would experience this g-force downwards here on Earth, that it would be equivalent to you weighing 9 times more than you actually do. And the reason that you pass out at such high forces, because at these forces your heart is simply not strong enough to pump blood through the brain, and thereby you pass out. Knowing this, the question is the following: how sharp of a turn can you make if you're traveling at these velocities, namely 2000 kilometers an hour, such that the fighter pilot does not pass out? So, such that the g-force he or she experiences is lower than 9. And the first step to any real-life problem or application in physics is to understand the question. What does it exactly mean? How sharp of a turn can you make? What exactly is a turn? Well, a turn is basically a change of direction of velocity. And to do this, we need to follow a curved path. In this case, a curved path that brings our direction of velocity from going forward all the way to going backwards, so 180 degrees. And it turns out that the optimal curved path, such that we are sure that the g-forces do not cross a certain boundary, is a circular path. This means going from the forward direction all the way on half a circle to the backwards direction. And this curved path basically is half the circle with radius r. If you would just complete the circle, it would look something like this. So what then determines how sharp a turn actually is? Well, if we compare this turn right here, which is half a circle of radius capital R, with another half a circle, for example this one, which is half a circle with radius small r, then we define the sharpness of our turn as the radius of the half circle trajectory that we take to make this turn. We can imagine, of course, that with a same velocity of 2000 kilometers an hour, the fighter pilot will experience much more g-forces in a very sharp turn than it would in a very large turn. And the question that we're trying to answer in this exercise is what r will be the minimal r, so the sharpest turn, such that we have a g-force of 9. And this is exactly what we will solve right now. Because we're looking at what the g-forces would be when we're making a turn on a circular trajectory, we can model our problem as a problem about uniform circular motion. And to do this, we of course first draw our circular trajectory. And on this circular trajectory, we now have our plane, which I simply draw as an arrow right here. And we see here, of course, that if we want to make a turn of 180 degrees, we will have to go all the way around half this circle. Let's define the radius of this circle as small r, which we need to find, of course. We know that the magnitude of the tangential velocity in this case is simply equal to the magnitude of the velocity of our plane, this being 2000 kilometers per hour. We know in uniform circular motion that we always have a centripetal acceleration, and this centripetal acceleration will always be pointing towards the center of the circle. So here will be AC. And with this AC comes the centripetal force, of course. And we know that the magnitude of this centripetal force is equal to m multiplied with the magnitude of the centripetal acceleration. And as we have seen in the initial brief overview, we know that the magnitude of the centripetal acceleration is equal to the tangential velocity squared divided by the radius of this circle. And it is now exactly this radius of this circle that determines the sharpness of our bend, such that this centripetal force is no larger than 9 times g, or 9 times the force of gravity. Therefore, we can write that in the extreme situation, the centripetal force, or the magnitude of the centripetal force, can only be m times g, so the magnitude of the gravitational force, times 9, so basically 9g. And at this point, we can simply solve this equality sign between these two sides of the equation right here, which is what we will do right now. So we have that the centripetal force is equal to m times v squared divided by r, and this has to be equal, in the extreme case, to 9 times the force of gravity, which is 9 times m times g. And again, what we need to find is this r right here. We see already that we can drop the mass on both sides of the equality sign, such that we don't really need to know the mass of this F-18 fighter jet. Rewriting this equation, we get the following. R is equal to v squared divided by 9 times g. And because we know the velocity, which is 2000 kilometers an hour, we know g, which is just the gravitational constant of 9.81 meters per second squared, and this 9 is just a number, such that we can actually calculate this r, which corresponds to the smallest turn that we are allowed to take. So we know that this will be equal to 2000 kilometers per hour squared divided by 9 times 9.81 meters per second squared. And at this point we see that we still have to adapt the units, because in the denominator we have meters and seconds, and in the numerator we have kilometers and hours. So what we're going to do is write these kilometers per hour as meters per second. And this we do in the following way. R is equal to 2000 multiplied with 1 kilometer is 1000 meters, divided by 1 hour is 3600 seconds. And we, of course, should not forget to square this numerator. And we divide this by 9 multiplied with 9.81 meters per second squared. And we see at this point that the units actually check out, because we see that we want the units of distance, which is meter. We see that this second squared and this second squared drops out. And we see that we have meter squared in the numerator and simply meter in the denominator. And therefore, what we're left with is only meter in the numerator. Therefore, we have 2000 multiplied by 1000 divided by 3600 divided by 9 multiplied with 9.81. We have to, of course, square this numerator, and our units are simply meter. Throwing this in a calculator, we find our end result of 3495 meters. And now we have to remind ourselves what this actually is. This is this radius right here, the radius of the circle along which our airplane makes a U-turn. This also means that if a fighter jet needs to make a sudden U-turn, it will end up 7 kilometers away from the initial point from which it started. For instance, if a fighter pilot will make the U-turn in the vertical direction and thereby gaining altitude, it will end up at an altitude which is 7 kilometers higher than it initially started with, and thereby almost gaining the same height as Mount Everest, just by making a U-turn. Let's go to the second exercise, where we're going to look at why the rotation of the Earth makes it so that by moving from the equator to one of the poles on the Earth's surface actually makes you lose weight. Or put differently, that the same mass will have a different weight depending on where you stand on the Earth's surface. And all of this only due to the rotation of the Earth. And before we exactly calculate by how much your weight reduces, let me first make a note on the difference between mass and weight. Mass is an inherent property of a specific object. It's basically the amount of stuff in it. It does not change depending on where you are in the universe, and its units are kilograms. Weight, on the other hand, is only due to gravity, and it's the force that an object exerts on the surface at which it is standing due to gravity. And because it is a force, it is expressed in newtons. The first step in this exercise is to consider the fictitious scenario where the Earth is not rotating, so it's basically stationary. In this specific case, your weight is simply the measured force that you exert on the Earth's surface. If you were to put a scale underneath your feet, then the weight is simply the force that these scales need to exert onto your feet to prevent you from falling through. In other terms, the weight that you experience on the surface of the Earth is simply the normal force. It's just another name for it. So what force does this weight force need to balance? Well, the only force that is present in this system is the force of gravity of the Earth that is pulling onto your body and is pointing straight towards the center of the Earth. Therefore, we know that the magnitude of your weight is equal to the magnitude of the force of gravity. The force of gravity is simply equal to the gravitational constant g multiplied with your own mass, multiplied with the mass of the Earth, divided by the radius of the Earth squared. And as you know, we can bunch some terms together here to write this gravitational force, or in this case your weight, as simply being your own mass multiplied with the gravitational acceleration g grav. And if we compare these two terms, then we see of course that our gravitational acceleration is equal to these constants right here. This means that in this fictitious case of a non-rotating Earth, if we can measure the gravitational acceleration, or the acceleration that a falling object experiences in this case, we can determine the Earth's mass, given that we know its radius and this constant g right here. So to recapitulate, in this fictitious case of a non-rotating Earth, things are very straightforward. You simply measure your weight, and the magnitude of your weight is exactly equal to the force of gravity, since this is the only force present in this system. Now we know of course that the Earth is not stationary and that it is rotating around its axis. So let's consider this scenario in scenario B, where we look at a rotating Earth. And also in this scenario, let's say that you're standing on the surface of the Earth, but now consider the fact that you're standing on the equator and the Earth is rotating around its axis. When we start from a non-rotating Earth and we start spinning it around this axis, when you're standing on this surface, you will notice that your weight will be reducing. If you would be standing on a scale, of course you will see that the scale will indicate a lower and lower number. And you can convince yourself of this process by considering the extreme case where we would be spinning up the Earth faster and faster until the point where you're actually floating just above the Earth's surface. And if we then start spinning even faster, you would be flung right into space. Well, this is extreme, but it's just to say that if the Earth is rotating, that your weight will reduce, because this is exactly what circular motion does. It just tries to keep you in a circular orbit, but you really just want to go in a straight line. And from this spinning thought experiment, we can conclude that if the Earth starts rotating, the measured gravitational acceleration, so the rate with which objects will fall towards the ground, will actually diminish and will be smaller than the actual gravitational acceleration that we calculated using the Earth's mass. Or in other words, the scale that you would be standing on will depict a lower number. This also means that if we would be measuring the gravitational acceleration here on Earth, which is evidently really rotating, then we would be measuring a gravitational constant that is smaller than the actual gravitational constant that would correspond to the Earth's mass. This means that if you would be deriving the Earth's mass from the gravitational acceleration, as I indicated in scenario A, that we would actually get a smaller mass because we would measure a smaller gravitational acceleration. This in turn means that the mass of the Earth is actually larger than measuring the gravitational acceleration will bear out to be. And this in turn is of course because it also needs to prevent you from flinging into space. Or in other words, the mass of the Earth also needs to act as the centripetal force, which is the force that keeps an object in a circular trajectory. And the question now is, how does this measured gravitational acceleration on a rotating Earth connect to the actual gravitational acceleration, which is a result of the Earth's mass? And this is exactly what we will calculate right now. Because you're standing on the surface of the Earth, and the Earth is rotating, you will be describing a circular trajectory. And we know that a circular trajectory requires a centripetal force to keep you there, because this force constantly changes the direction of your velocity. And fortunately, we now have an expression for the centripetal force. We know that the magnitude of the centripetal force is equal to your mass times the centripetal acceleration, and the magnitude of the centripetal acceleration is equal to the velocity squared divided by the radius. Or if we write it in terms of the angular velocity, which is 1 revolution per day in the case of the Earth, we get that the magnitude of the centripetal force is equal to m, the mass of your body, multiplied by the radius of the Earth, multiplied by omega squared, which is the angular velocity squared. And this is exactly the force that is needed in order to keep you on the circular trajectory on the surface of the Earth. Therefore, we know that the gravitational force, which is only due to the mass of the Earth, has to be equal to the measured gravitational force if we would wrongly assume that the Earth is not rotating. However, the real gravitational force, f of g, also needs to overcome the centripetal force and thereby keep us in our circular motion or prevent us from flying off into space. Now, most of you are probably more familiar with fictitious forces, which would say that the measured force that we measure on the surface of the Earth is equal to the magnitude of the gravitational force, which is due to the mass of the Earth, minus the centripetal force, Fc, which is basically just a rearrangement of these three terms right here. However, in this framework, we say that this force right here, which we subtract from the gravitational force, is a centrifugal force, which is then said to be a fictitious force because there is no force that is pulling you away from the Earth. It's simply you wanting to go in a straight line, which any object in motion actually wants. And because calling into life forces that do not really exist, I avoid using fictitious forces. Thereby, let's use this intuitive equation, which says that the force of gravity due to the Earth's mass is equal to the force of gravity if our Earth is not rotating, and the centripetal force, which is present because we are rotating. We know that the force of gravity is equal to the mass of our body multiplied with g gravitational. And again, to be sure, this is the gravitational acceleration, which is only due to the mass of the Earth, which is not what we measure in experiments here on Earth, because the Earth is also rotating. This is equal to the mass of our object again, multiplied by the measured gravitational acceleration, which is a combination of the acceleration due to the Earth's mass and of the rotation of the Earth. And the magnitude of the centripetal force due to the rotation of the Earth, we calculate to be m multiplied by omega squared multiplied by r. We see here that our mass does not matter in this entire story, and it holds for any mass, because we see that mass cancels out in each of these terms. So let's now fill these quantities in. We have the g measured. If you look it up, or you can measure it yourself by dropping objects from different heights, is 9.81 meters per second squared. This is the acceleration that we measure when we are dropping objects here on the Earth's surface. Then we add to this the radius of the Earth, which is 6,370 kilometers, or we can add 3 zeros to make it meters, because 1 kilometer is 1,000 meters, multiplied with the square of the rotational speed of the Earth squared. Now, what is the angular velocity of the Earth? It's simply 1 revolution, or 2 pi radians, in 1 day. Now, 1 day is 24 hours, 1 hour is 60 minutes, and 1 minute is, of course, 60 seconds. So we multiply 24 times 60 times 60, and we have seconds. And we square this, of course. Checking, of course, the units as good physicists, we see that we need an acceleration on the left-hand side, and therefore we also need the units of acceleration on the right-hand side. We have meters per second squared here, and in the second term we also have meters divided by second squared right here. So the units check out. So let's now calculate this even further. We get 9.81 9.81 meters per second squared. And if we run this second term through a calculator, we find 0.034 meters per second squared. And adding these two numbers together gives us the total gravitational acceleration if the Earth were not rotating. And this becomes 9.844 meters per second squared, which is our result. And thus we have found the connection between the measured acceleration of dropping objects here on Earth and the acceleration due to gravity. And we see, of course, that the measured acceleration, 9.81 meters per second squared, is smaller than the actual acceleration that we would expect from gravity if the Earth were not rotating. And this term here that takes into account the fact that we are rotating and thereby having less weight on the equator is approximately 0.35%. Therefore, going from a rotating Earth to a non-rotating Earth, we need to add 0.35% to our weight. And because the weight is what determines which number appears on a scale, we see that if we go from a rotating Earth to a non-rotating Earth, the scale will show a number which is 0.35% larger. Now you might find this a very absurd exercise because after all, our Earth is always rotating. We don't have a non-rotating Earth, so why does this all matter? Well, consider the following scenario. Let's say that you're standing on the equator, which means that the acceleration that you measure is 9.81 meters per second squared. And therefore, let's say that at the equator, the scale on which you are standing would present 70 kilograms. Alright, this is all fine, but let's now consider if you would be traveling to the North Pole and you would be standing exactly at the North Pole. Well, let's remind ourselves that at the North Pole, you're actually not rotating because it is exactly at the North Pole that the rotational axis crosses the Earth's surface, and thereby there is no rotation on the surface of the Earth at both of the poles. This means that at the North Pole, the gravitational acceleration is only the gravitational acceleration due to gravity, which we have calculated to be 9.844 meters per second squared, which is an increase of 0.35%. And this in turn means that if you use the same scale and you didn't lose any mass yourself, that the 70 kilograms, if put on the same scale at the North Pole, would now return 70.245 kilograms, or an increase of 0.35%, or an absolute increase of 245 grams. And in this sense, you actually gained weight as far as the scale is concerned by moving from the equator to the North Pole. And this only due to the fact that the Earth is rotating. And of course, vice versa, if you don't like the number you see on your scale, you can simply move closer to the equator and thereby reducing this number by simply rotating at a faster speed through space. And this brings us to the end of this video, and I hope that you're now more familiar with how the centripetal force works. If you have any questions, leave a comment in the comment section below or join our Discord server. If you like this video, give it a thumbs up, and if you want to see more in the future, consider subscribing. And with that, I thank you for watching and sticking out this video, and I will see you in the next one. Bye.